Hello everyone, I'm Frank, and welcome to Frank Puzzles, and this is today's hard level difficulty puzzle. And it's called Rat Run 33, Hot and Cold, by Marty Sears. And here are the rules. We have normal Sudoku rules apply, which means in every cell in the grid, place a single digit such that every row, column, and designated 9-cell region contains the digits 1 through 9 exactly once each. Aim of experiment. F and P must both reach different cupcakes by finding a path through the maze. The paths must not visit any cell more than once, share cells, pass through any thick maze walls. It does not say that they can't cross. That's interesting. So for the paths for F and P, I guess we'll make this F and this P. I don't know. We need to both reach different cupcakes by finding a path through the maze. And the paths cannot visit any cell more than once, share cells, or pass through any thick maze walls. So you could do something like this. And let's try to... So I guess you can cross, though. That is interesting. So you could potentially do something like this. As long as they don't share cells. And they can't cross through any thick maze walls, which means you can't go this way. But those are the restrictions, interestingly enough. Usually it's that you can't cross either, but in this case, it specifically does not say that. So they possibly could cross here. Anyways, get to the rest of the rules. We have hot and cold zones, where we need to divide the grid into 2 zones of orthogonally connected cells, one hot and the other cold. And no 2x2 area may be completely in one zone. So that means this is a yin-yang shading. So we need to divide the grid into hot and cold zones, which are orthogonally connected. Now, what does it mean to be orthogonally connected? It means you can go from any cell in one region or in one zone and go to any other cell in that zone just by going through edges, all while staying within the zone. So for example, to get from this cell to... This is an example of a valid yin-yang shading, or hot and cold zone shading, I guess. Where... I guess we can make this red. Where in the blue zone, to get from any cell to any cell in the... From any cell in the blue zone to any other cell in the blue zone, you could go along edges while staying within the region. For example, to get to here, you would go along these edges here while staying within the blue region. Same for the red zone. To get from this cell to this cell, you can go along these edges here to just stay within the red zone while going between cells. And... what is an example of an invalid shading? It would be something like, say, this. Oh, why can't I click on that? Okay, there we go. What? No, it's not allowing me to click. What the heck? Why isn't it allowed? Oh, because I'm going back. Never mind. I'm undoing. Apologies. Anyways, okay. Now the problem here is for the red zone, you can no longer go from these cells here to these cells here just by going through edges while staying within the zone. You have to either go through a corner or go through an edge and exit the zone, which is not allowed. So that's why this is an example of an invalid shading here. This is also an example of an invalid... Actually, let's use this one. This is an example of an invalid shading here because this 2x2 area is completely in one zone, which is not allowed for either the red or the blue zone. for any 2x2 area. So that's an example of how hot and cold zones work. We have invisible walls, where a fuse maze walls are visible, right? We only have 4 of them. But the rest are invisible and must be located. Okay. If 2 orthogonally adjacent cells are in different zones, a wall exists between them. If they are in the same zone, no wall exists between them. And orthogonally adjacent cells are just cells that share an edge. That's another way of putting it. So these 2 cells are orthogonally adjacent, so are these, so are these. So if 2 orthogonally adjacent cells are in different zones, a wall exists between them. If they are in the same zone, no wall exists between them. Because no 2x2 spaces exist fully within one zone, no diagonal movements are possible in this maze. So, for example, then, if we had these as the actual zones, you would have to have a wall going this way. Obviously, there's some problems with that, right? But that's how these invisible walls work. Okay. Box balance. We have the values of a hot cell equals its digit plus 1, and the value of cold cells equals its digit minus 1. And in each 3x3 box, the total values of hot cells must equal the total value of cold cells. So, for example, in box 1, obviously this is going to be problematic, but, well, actually, is it? Maybe not. The value of these cold cells must equal the value of these 2 hot cells. And that's for every 3x3 box. So that could actually work, because the hot cells gain plus 1. Okay. We also have courants, or currents, as normal people say it. I don't know. When I first started doing these, I didn't know how it was pronounced, so I just pronounced it to myself as courant, as like a sort of Frenchified way of putting it. It's not, though. I don't know why I did it that way. Anyways, but I got into the habit of saying that, so apologies if you're irritated if I mispronounce it, which I sort of deliberately am right now. Anyways, if a black courant sits between 2 cells, then the value of one is double the value of the other. And remember, these are the values of hot and cold cells. So, for example, you could have something like, say, 5 here and 4 here. The value of this cell would then be, and if assuming this is the correct hot and cold shadings, which is probably not, which is definitely not, in fact, this value would be 5 plus 1, because it's a hot cell, and that's 6, which is in a 1-to-2 ratio with this value, which is 4 minus 1, since it's in the cold cell, which is 3. So that actually works there. So for a black courant, then the value of 1 is double the value of the other, which would work here because 6 is double the value of 3. If a red courant sits between 2 cells, then one has an odd value and the other has an even value. And 2 cells joined by a courant are both in the same zone. Interesting. Okay. Huh. That is interesting, actually. So there's no way that this actually can work because they have to be in the same zone. You can't be in different zones if you have a courant between them. Okay. Test constraints. P must stay in the hot zone and F must stay in the cold zone. Well, that was sort of necessarily I guess it wasn't completely given. They could have both been in the hot zone or both been in the cold zone too. But one of the rats is going to be in the hot zone and one of the rats must be in the cold zone. And those are all the rules. If you'd like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's go. Okay. Um, So we know these are on the same zone. This is a 2x2 area, so this must be a different zone here. So we know there's a boundary invisible wall there. Same with this. This is all in the same zone because courants separate our cells set joined by courant are in the same zone. Same with these. So these must be two different zones because otherwise if they're the same zone, you'd have a 2x2 space that would be all the same zone, which is not allowed. Same there. Same here. uh, let's see. These again must be different zones because then you'd have a, if they were not, these would all be the same zone and you'd have a 2x2 area that's all the same zone, which is not allowed. Um, hmm. Um, what else do we know? Okay, so for hot zones, what digits can be in 1 to 2 ratios with each other? Actually, let's do cold zones. So that means that the digits, it's the values 0 through 8. So you still have 1 and 2 can be in a 1 to 2 ratio, 2 and 4, 3, 6, and 4, 8. So those can all still be in a 1 to 2 ratio. So that would be what values can be what values can be in the same row or column, sorry, in a 1 to 2 ratio with two unique digits. For the cold zone, instead of 2 and 4, it would have to be 3 and 5. So, okay, that's interesting then. So, what about hot zones? Hot zones, you have, instead of the values 1 through 9, you have the values 2 through 10. So the digits in a 1 to 2 ratio are 2, 4, 3, 6, 4, 8, and 5, 10. Interesting. So you're guaranteed still only two unique digits can be in a 1 to 2 ratio with only two digits, two values I should say, can be in a 1 to 2 ratio with two other unique values. And that's the values of 2 and 4. For the cold cells, then, the cells would then have to be 3 and 5. But for the hot cells, 2 no longer is in a 1 to 2 ratio with another value. It only is in a 1 to 2 ratio with 4 because we don't have the value of 1 in hot cells. So that means it would have to be value 4 and would have to be 3 guaranteed. So these then that are in a 1 to 2 ratio with 2 unique values, which these have to be because they join cells in the same region or in the same zone. So these have to be 3 or 5. Well, the interesting thing is this 3-5 pair eliminates 3 and 5 in the rest of the column. So for this to be in a 1 to 2 ratio for these values, if this were to be a hot zone, the problem with that is that it would have to be 5 No, if it's in a cold zone. If this were a value in a cold zone, it would have to be... Hold up. No, okay, could be. I was thinking something else, but I don't think that works. Right, so cold zone, so the values next to a black Kropke dot in a cold zone are, instead of 1, 2, 3, 4, 6, and 8, they are 2, 3, 4, 5, 7, 9. Okay. And for a hot zone, what can they be? In a hot zone, they could be, so it's values of 2 and 4, 3 and 6, 4 and 8, or 5 and 10. Well, that's 1, 2, 3, 5, 7, and 9. So these have to be 1, 2, 3, 4, 5, 7, and 9. We cannot have 6 or 8 next to a black Kropke dot, interestingly enough. Okay. So these are guaranteed to be 1, 2, 3, 4, 5, 7, and 9. This 3-5 pair in column 9 eliminates 3 and 5 in the rest of the column. Okay, so if this were hot, you can't have 3 here. Actually, you would have to have 3 there. Right, so if this is hot here, it has to be 3, which is the value of 4, in a 1 to 2 ratio with 2 and 8. Because you don't have a 3 or 5 available here. Actually, it doesn't matter. It's always going to be the case for that. Which would mean that's the digits 3, 1, and 7. Okay. But if this is cold, the problem is you can't have the value, you can't have 5 there as a cold, because that would be value 4, which is in a 1 to 2 ratio with the values 2 and 8, which would force this to be 3 and 9, but we don't have 3 available here. So either way, I think this is guaranteed to be a 3 then, which makes this a 5. Right. So therefore, this is 3, and this is 5. 5 cannot be in a 1 to 2 ratio with two other unique values unless it's a cold zone. So that would be 5 minus 1 is 4, which is in a 1 to 2 ratio with 2 and 8 in value, which is 3 and 9 as digits. 3 can't be here, so this must be 3 here, and this is 9. That eliminates 3 and 5 here. That's interesting. So 3 eliminates 3 in the rest of the column here. This can't be 9 here. 3 here eliminates 3 in the rest of the box here. So can this also be in a 1-2 ratio? So for lows again, one obviously can't be here. So if these are both lows, well, this can't be 9 because of 9 in the box. If this is both lows, that would mean you can't have 1 or 2 because that's value 0 and 1. 1 has to be in a 1 to 2 ratio with value 2, but that's 3, which we can't have. Sorry, digit 3. 4 would be, so it would have to be 4 and 7. Because that's values 3 and 6. Digit 9 gives you value 8, but we don't have the value 4 available anymore. So if these are both cold, it's 4 and 7 as a pair. If they're hot, 1 would jump up to 2, but we don't have a 4 to be in a 1 to 2 ratio. We don't have a value of 4 because the 3 is taken. 2 would go up to 3, but we don't have a 6 in value because the 5 is taken. 4 would go up to 5, which could be in a 1 to 2 ratio with 9. So we could have... So I think we're guaranteed one of these is a 4 then, right? 7 would jump up to 8 in value, which we don't have a 4 in value anymore because the 3 is taken. So we're guaranteed a 4 here. What about if this is hot and this is cold? If these are hot, we have 3 available. 3 would have its value be 4. So that would be 2 and 8 in value. So 2 and 8 in value would be 1 and 7, so that works. If, on the other hand, 3 is cold here, that would mean its value is 2, so that it'd have to be in a 1 to 2 ratio with 1 and 4 in value, which would have to be 1 and 5, or sorry, 2 and 5 for digits, which doesn't work. So this must be all hot. Interesting. So we have switched cold to hot here. Which means, first of all, these are cold because they must be the same zone. This must be hot because we have 3 digits in that zone there. So we can remove these because, well, actually we should just keep the walls because these are walls. Interesting. Remaining digits in column 9 are 2, 4, 6, 8. Interesting. Hmm. We know these two are the same zone because that rat must be able to exit out. Um, this is interesting. Remaining digits in row one have to be 1, 2, 6, 7, 8, and 9. For yin yang shading, you can only have two changes of shading on the edge of the grid. So we already have one between these cells. And therefore, somewhere along here, there must be one between these cells, but we don't know where. So once we figure out that one, that should help. Huh. I'm getting a spam call. We'll just ignore that for now. Um, let's see. What else do we know? The value, so again, the constraint is the values of the, in each 3x3 box, the values of the hot and the cold cells are equal. Okay. So we don't know if this is a wall here or not. We know the cold cells already add up to, it's 2, 4, and 8. So it's 16. But that doesn't really restrict very much, right? The hot cells has +1 in them, in value. Um, hmm. 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 Um, if these are both hot, hmm. What are the values? We don't have 3 available. So that means no 4 in value. So you can't have 2 in value with that. You could have 2 and 5 as a pair, so that's values 3 and 6. We don't have 4 available. Or you could have 4 and 9 available for values 5 and 10. Um, hmm. If they're cool or cold values, you don't have 1 available again. Actually, that wouldn't be available anyways. Um, you can't have 2 and 3. Um, because that would be values 1 and 2, but we don't have the 3 available as a digit. 2 and 4 again doesn't work because we don't have 3 available. 3 and 6 would be available as 4 and 7, so that could work. And then 5 and 9 works as 4 and 8 in values. So that's kind of varied there too. um, 9 eliminates 9 here. Huh. So this is the same here. This doesn't have 3 available, which gives in hot zones the value 4, so therefore this can't be 1, and in low zones 1 would be value of 0. So these are the same essentially values here and here. Or they could be. They don't necessarily have to be. Um, Well, we know P or whichever rat is here has to go that way. We don't know where this rat goes. Uh, hmm. 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 Can we actually have two hot digits equal the same sum as all the rest being low digits? Two hot digits would be 8 and 9 at minimum. Sorry, at maximum. Plus 2, so that would be 19 in value. The rest of the digits would be 1 through 7, which is 28, subtracting 7, which is 21. So no, you cannot have 2 hot zones with 7 cold in the same box, 3 by 3 box. You have to have at least 3 hot digits. How many at cold digits can you have? Or what's the minimum amount of cold digits can you have in the same box? Um, hmm. Can you have 4 cold digits? I think the answer to that maybe, well, actually, I don't know. 6, 7, 8, 9 would be the max cold digits. That's 30 minus 4, so that's 26. Plus the hot digits would be 5 hot digits, which is 1 through 5. Adding 5 is 20. So that could be the case. We could have 4 cold digits. Can you have 3 cold digits? I think the answer is no. 3 cold digits is 7, 8, 9 at max. Minus 3 is 21. And then 1 through 6 at minimum, which is 21 already, plus 6 adds, yeah. So you can't have, okay. You can't have 2 hot and 7 cold in the same box. You can't have 3 cold and 6 hots in the same box. So you have to have at least 4, you have to have at least 3 hots in a box and 4 colds in a box. Interesting. So that means this cannot be all hots. So if we had a hot here, that would guarantee all of these are hot because again, you can only swap. Okay, you can swap. Sorry, I didn't say it correctly. You can swap 0 or 2 times on the edge of a grid for yin-yang shading. And the reason is because if you did more than, well, you can't swap only once because then you have to swap back somewhere else. So you're always swapping in sets of 2s. So there are always an even amount of swaps. And if you try to have more, so say you had this red, blue here. If you orthogonally connect the blue cells, you would automatically break the red cells into 2 separate regions, which is not allowed. Same with the red cells if you break that into 2 cells. So, if these are red, you have to stay red all the way here, which would mean these are all, this is blue. And the problem with that is these both would be blue. Only one of these could be blue here. You couldn't have 2 blues here. So that would be 4 blues in the box. Or sorry, you couldn't, 3 blues in the box, which can only have values 7, 8, 9 at most, 24 minus 3, because minus 1 for each digit, and that's 21. Whereas the 6 reds in the box would be adding up to 21 already for the digits, plus another 6, which is 27. So therefore, this cannot be, this specifically can't be red. If this is red, all of these are red. You'd have to have blue here. Only one of these could be blue, so that's only 3 blues in this box, which is not allowed. So this cannot be red. This must be blue, which means blue has to go all the way around this way. That makes this red as a pair. That makes this red as a triplet. So therefore, these are all walls. Oops. So these are walls. This is a wall here. These are both blue, so this can't be blue here. It must be red. Because then this 2x2 area, same with this. These are red. So these 2x2 areas have to be all red. These are blue. So, in a 1-to-2 ratio in the hot digits, it has to be 2, 4, and 8 only for the values. So that means it has to be 1, 3, and 7. So again, this is 3. This has to be a 1, 7 pair here. So this can't be 3, 1, or 7 remaining in the rest of the column. No 3, 1, or 7. No 3 here because of 3 in the box. So 3 cannot be here. Because if 3 were here, it has to be in a 1-to-2 ratio with the values 2 and 8. But that's 1 and 7, which we can't have there because of the 1, 7 pair in the column. So again, the values have to be 2 and 4, which can't be possible here because we can't have 2 or 4 there. We can't have values 2, 4, 8 here. These are values 3, which would have to be 3 and 6, so that would be 5. 4 would be value 5 with 9. 5 would be value 6 with 2, which is value 3, and 9 would be value 4 there. Okay. These are cold, though. So, we have 3 hots. Okay, there's no way, again, in every box, you have to have at least 3 hots. So therefore, this is hot here. What is the values that we can have? Well, 6 colds. If we have 1 here, that means this is at most 1, 3, and 9. 1, 3, and 9 is at most it's 13. 13 plus 3 is 16. 45, which is the digits 1 through 9, subtracting out 13 is 32. And then you subtract out 6, that's 26. So you cannot have a 1 here. This must be 7, which makes that 1. So no 1 here, no 7 in in this box. What digit has to be there to add up? Let's try 9. So 19 plus 3 is 22. The remaining digits is 45 minus 19, which is 26, minus 6, which would be 20. So this cannot be 9. Therefore, this is 8. So 3, 7, 8 adds up to 18, plus 3 is 21. So 45 minus 18 is 27 for the remaining digits. Minus 6 for the cold digits gives us 21. So this must be 8, which eliminates 8 in the rest of the box. Okay. These are cold digits in a 1 to 2. Oh, these are cold digits in a 1 to 2 ratio. It has to have 4, which is value 3. And that's in a 1 to 2 ratio with 6, which is digit 7. So they have a 4, 7 pair here, which eliminates 4, 7 in the rest of the row. So no 7 here. Whereas 8 in row 1, it has to be one of those 2 cells. Okay. We have to have 3 hots here. Because every box needs at least 3 hots. And so this one has to also be 3. Because it can't be 2 reds there, because that would force a 2 by 2 area that's all red. So then it has to be 3 only. And again, the combinations have to add up to, for the reds, it has to add, basically it has to add up to 21 on both sides. Which means for the digits themselves, they might, well, okay, let's just do non-digits. For non-digits, so let's just say values. Can we have 2 and 5 here? That would be values 3 and 6, which is too small. Because that's only 9 in value. We need to get to 21 with the single value. And the largest value we have is 10. So 3 and 6 does not work. We don't have 4 and 8 available, so it has to be 5 and 10 in value. So this must be then 4 and 9 as digits, which eliminates 4 and 9 in the rest of the row. So no 4 here. So that's value 5 and 10, which is 15. So we need a value 5, or sorry, value 6 for the other hot digits. So 5 has to be one of these digits, which eliminates 5 in the rest of the box and row. And this can't be 5, 4, or 9 because of the 4, 9 pair in the box. So this has to be a 2. That means this can't be 2 here. 2 is value of 1 as a cold cell. So it must be in a 1 to 2 ratio with value 2, which is 3. So this must be 2 and 3 here. That eliminates 2 in the rest of the row and 3 in the rest of the column here. So we have 5 here, 4, 5, and 9 add up to 18, plus 3 is 21. The rest of the digits is 45 minus 18, which is 27. Subtract out the 6 for the cold cells. So that's 21 also, and that satisfies that. Okay. We don't have value 4 here for this cold 1 to 2 ratio. So obviously you can't have 1 here. Can you have 2? 2 would have to be in a 1 to 2 ratio with... you don't have 3 here, sorry, which is value 2. So this can't be 2. 4 could be with 7 only. That's value 3 and 6. And then you could have 5 and 9 together as 4 and 8 as a pair. So this is either 4, 7, or it's 5, 9 as a pair. Either way, we are guaranteed one of these is 4 and one of these is 9. And since this is 4 and 9, that limits 4 and 9 in the rest of the column. So this can't be 4 or 9. These can't be 4 or 9. So this has to be what? 1, 2, no 3, no 4, 5, 6, 7, no 8 or 9. 1 cannot be either of these digits here because of 1 in the box. 2 can't be here because of 2 in the box. In fact, remaining digits in box 7 are 1, 5, 6, 7, 8. No 1 or 7 here because of 1 or 7 in the column. No 5 here because the 5 has to be in the hot digits here. Okay. Remaining digits in row 2 have to be 1 through 6. So no 3, 5 here because of the 3, 5 pair in the box. Huh. So we've got, okay, this can't be 3 because of 3 in the box. So remaining digits in this box are 1, 2, 4, 5, 6, and 9. Remaining digits of column 2. We have 4, 5, 6, and 9. 4, 5, 6, 8, and 9. Okay. Hmm. 3 in row 2 has to be one of these 3 cells. 8 in row 3 has to be one of those 3 cells. We don't know if we have. We don't know if we have wall here. Okay. Uh, uh. Hmm. Hmm. So again, at minimum, we need 3 hot cells and we need 4 cold cells in our region. In a box, I should say. In a 3x3 box. Hmm. Um. Okay. What happens if this is blue? Oops. If this is blue, so on in yin yang shading, if a diagonal is the same shading, you cannot have a diagonal of the opposite shading be on this opposite diagonal. So say we had a blue here and then a red here. That's not allowed because to orthogonally connect the reds, you would necessarily have to break the blue. So these are two deductions you can make about yin-yang shading. You can only have 0 or 2 changes of shading on the edge of the grid. And if you have a diagonal that's one shading, the other diagonal has to be the shading of one being the same shade and one being the opposite shade. And you can't have, obviously, the same shade here, because then this 2x2 area would be the same shading. If they're the opposite shadings, if you orthogonally connect the reds together, that will necessarily break the blues into 2 separate regions. If you orthogonally connect the blues together, that would necessarily break apart the reds into 2 separate regions, which is not allowed. So if we had blue here, that would force blue to be here. The most these hots could ever be would be 1, 7, and 9. Because we can't have 9 here anymore because of one of these is going to be 4 or 9, right? It's either 4 and 7, which would have values 3 and 6 in a 1 to 2 ratio, or it's 5 and 9. Because it can't be, we don't have available the value of 4, which is 3 in the column. So, that means this cannot be blue. Because if we have blue here, that forces blue here. That would mean these are red at best, which adds up to 1, 7, and 9, which is 17, which plus 3 is 20, but then the rest would be 6 digits, adding up to 45 minus 17, which is 28, minus the 6 for the cold digits, which would give you 22 as a value, which doesn't work. So this cannot be blue here. This is a red. So therefore we have boundary there. We have to have at least 2 reds here. We don't know where they are. I feel like I have to figure out these here. Hmm. So for 2 to be here, it has to be, it can't be a cold cell, because cold cell would be 2, which would be value 1 within a 1 to 2 ratio with 2, which would have to have a 3, which we can't have. So first of all, we know 3 actually is one of these 3 here. So it would have to be 2 as a hot with 5 in the other cell to be in 3 to 6 values. So 2 cannot be here. So this is guaranteed to be 5 or 7. That's interesting. So 2, again, value, it's a hot cell, 3 with value 6. 4 could be cold. And then that would be value 3 with the value 6 of 7 going down. Can 4 be hot? And the answer is no. So 2 would be hot with 5 hot. 4 would be cold with 7 cold. 7 cannot have... Oh... 7 cold would have to be with 4. 7 hot would have to be with 3, which is not possible. And this can't be 4, 3, so therefore this can't be 7. 9 would be cold with a 5. Or it could be hot with a 4, which doesn't work. Okay. Hmm. So these are either 1, 3, which is 2, 4 in value. 2, 5, which is 3, 6 in value. Or 3, 7, which is 4, 8 in value. Okay. And we know we have 1 odd and 1 even digit here. This is odd. This is an even digit. We know this is odd. We don't have very much other information, though. Okay. So if we have six blues and three hots in a box, the hots must add up to 18. The colds must add up to 27. If we have four hots and five colds in a box, four hots and five colds, the four hots have to add up to what? Is it 17 plus 4? Does that even work, actually? Hmm. Probably. Um, it can't be 18. It has to be 17, right? So the hots would add up to 17 plus 4 is 21. The colds would add up to 45 minus 17, which is 28. Minus 5. No, it's 16. No, it's 18. Is it 8? Is it always 18? So do the hots always add up to 18 is the question. Huh. Um, that's interesting. So if the hots always add up to 18. So 4 hots, 18 plus 4 is 22. 45 minus 18 is 27, minus 5 is 22. And then we have the other combination, which would be 5 hots and 4 colds. So if we have 18 hots, that would be 18 plus 5 is 23. The colds would be, again, 45 minus 18, which is 27. Minus 4 is 23. Right, so the hots always have to add up to 18, which is why we can't have 6 hots in a box. But that's why 3, 4, and 5 work. So the digits in the hot digits must add up to 18 no matter what. And the cold digits must add up to 27 no matter what. Interesting. So the hot digits are always 18. The cold digits are always 27. Just at summing up the digits. Hmm. um, huh. So the interesting thing here is if these are hot, you're guaranteed this is cold because of the 2x2 area. You're guaranteed this is cold by the 2x2 area. And you're guaranteed these are cold because of the connection of the 2x2 of this area. You can't swap more than 2 times on the edge of the grid in shading. If these are cold, these diagonals are cold. So if this is hot, you know these are cold, and that's cold. If these are cold, this diagonal is both cold, so we have to have a cold there. So no matter what, this is always cold here. You'd have hot and hot here, or so you'd have cold and cold here. Hmm. Okay, so if this is hot, then the rest of this box is cold. What does that mean? You can't have 4 and 9 here. What would that leave? 2 and 5 work, and that's it. Right? So if these were both hot, um, 4 can only be with 4 would be have value 5, but that can't be value 10. 9 would be value 10, and that can't be value 5. So it would have to be 2 and 5 here, which is value 3 and so 2 and 5 adds up to 7. You need to add up to 18. The problem is that these two don't add up to 18. It would have to be 11, right? So 2 and 5 is value is for the digits it's 7. 18 minus 7 is 11, but there's no way this can add up to 11, right? Without with 5 gone and 2 gone. It's going to be hard. So therefore this cannot be two hots. It has to be two colds. Interesting. This could be cold here, but if this is cold, this can't be cold. So this is guaranteed to be hot. So this is definitely hot here. This must go connect some way out here. So this must be hot here. And we could just have this rat be going that way. Or we could connect that way. We don't know. So this must be cold. So 2 would be value 1, which cannot work. You could have 4 here with value 7. So digit 4 and digit 7 is value 3 and 6. Digit 9 and digit 5 is value 8 and 4. So that could work. Okay. Okay, so we know there's a wall here. Could have wall here. Therefore, this path has to go this way. So we'll mark that as red. It could just be from this rat there. My guess is that's probably not the case, but don't know. Hmm. 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 This is one odd, one even digit there. Hmm. 3 has to be one of these 3 digits there. Hmm. We could have blue, blue there if this is red going out. Hmm. This is red, so this cupcake must be blue here. Okay. Hmm. Um, we have one odd and even digit here. Hmm. If these were both hot cells, that means these must add up to 27 as digits and would be cold. Hmm. So if these are both hot, we could technically have one. No, we can't. We have to have four colds guaranteed. So this would be cold, cold, cold. Ah, well, I guess you could go hot, hot there, technically. It's just that this rat would have to go that way. I was just thinking to orthogonally connect, you have to go that way. Hmm. What does that leave? Okay, so if this is both hot, again, in this box, we have to have four colds in a box. Because to add up to 27, you can't have three digits adding up to 27. Um, so you would have to go hot then hot here. So that would guarantee that that digit is hot. If these are both cold, this area is a 2 by 2 that's all cold. This has to be then hot. We have to orthogonally connect the hot, so therefore hot would have to go there. So this is guaranteed to be hot no matter what. So we know that's hot. We could have another hot here. We don't know how that works. Or it could be cold. We're not completely sure. Um. Hmm, 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 hmm. So what happens if we have two hots here? Um, the rest must be cold. Since those are cold, that means hot has to go this way. This is a diagonal of two cold, so cold has to go there. Hot has to connect this way, diagonal of cold, hot here, so that would force hot to be there. No hot here, so that's cold. 3 by 3 that or 2 by 2 box that has 3 cold, so this is hot. Diagonal 2 hot, so this must be hot. 3 by 3 that has 2 by 2 that has 3 hot, so this must be cold. This is hot, so these must be cold. And we have a diagonal here of cold, a diagonal here of cold. This is hot, so this must be hot there. That makes this cold. 3 by 3, that is all cold, so this must be hot. Diagonal of 2 hot, so therefore this must be hot because we have a cold there. Okay. So far, this looks okay. Um. Hmm. One of these has to be cold, one of these has to be hot. Because we have two hots here and two colds here. If both of them were the same shading, you'd have a 2 by 2 that's going to be one of the shadings. Hence we know it's a blue-red pair here. Um, Hmm. That seems fine so far. Hmm. Hmm. Yeah, this seems fine. Hmm. Huh. I was hoping we'd get to contradiction, but right now we don't seem to be running into that. We guaranteed this is hot. If this is cold, that leaves. Oh, either way. So if this is hot, that means this is cold, cold. That's 5 hots in the box. If this is cold, these have to be hot, hot because of the 2x2 boxes that are all cold. So either way, box 6 is going to have 5 hot digits. And you add up to 18. Um, can you have 7? I don't think you can. Can you have, sorry, in the hots, can you have 7? So 3 and 7. I guess you can. It's 125, right? For the remaining digits. Um. Hmm. Interesting. So you could have 1, 2, 3, 4, 7. 1, 2, 3, 4, 8. 1, 2, 3, 5, 7. You're guaranteed a 3. So that means the other 4 digits must add up to 15. So that's 1, 2, 4, 8. 1, 2, 5, 7. Huh. Hmm. Does that help any, though? I don't know. Okay, let's have. What happens if we have blue here? Then this is red, this is red. This 2x2 area, it's all red, so this must be blue. Um, only one of these can be red, and we have to orthogonally connect out. Mm -hmm. Not too helpful, unfortunately. I thought it would help there somewhat, but probably not. Can we have 4 9 could work. Hmm. 27? Actually, does it work? 4 9 would add up to 13. So the remaining digits would have to be 6 and 8, but that's not going to be an odd-even pair. They're both odd values because of the -1. So 4 and 9 does not work here as a cold. Actually, no, it'd be 5 and... Okay, 5 and 9 could work. 4 and 9 cannot work as a hot. But it could work as... 5 and 9 could work as a cold. So that works there. 2 would have to be a hot with 5, but that does not work. Because we would have to have 1 and 7 as the rest of the hots. And this can't be 1 or 7 because of the 1-7 pair in the column. Huh. Right, so the hots must add up to, again, 18, which is an even sum. Hot digits must add up to 18, which is an even sum. These are both even. And this is even. Sorry, these are both odd, which adds up to an even sum. Plus an even value is an even sum already. So if these were both hot, they would both have to be an even sum for the digits. But that's guaranteed to not be the case. Because... Is it? Hold up. No, that's not necessarily the case. Well, that is necessarily the case. So the possibilities we have here for the hots being there are 2 and 5, which is the values 3 and 6. But the 2 and 5 require specifically 1 and 7 to add up to 18 as a pair. And this can't be 1 or 7 because of the 1-7 pair in the column. Or you could have 4 and 9 here, which is values 5 and 10. But the problem is that's too big because 1, 2, 3, 4, 9 adds up to 19, which we need to add up to 18 for the hot digits. So that eliminates both hot possibilities, which means these are both cold. Which means this 2x2 area is cold, which makes that hot here. This 2x2 area has 3 colds, so that must be hot here. That means this 2x2 area is all hot, which means this must be cold. And we now know that this is P, we must stay in the hot zone, and F is the upper right-hand rat. So she has to go this way. P has to come from this route and go that way. You can't have 2 here anymore. That's a value of 1, which can only be in a 1-to-2 ratio with a value of 2, which we don't have in that box. And we know this is an odd-even pair of digits. So because of that, since this is an odd-even pair of digits, that must be an odd sum for the digits, and it must add up 27 for the cold digits. 27 is the odd sum. So an odd sum here plus an even sum adds up to an odd sum, so these both must be even. So, sorry, it must be an even sum, which means 4 is not allowed there. So that means it can't be 3, 6 as a 1-to-2 ratio. It's 5, 9. That's 14, so these two must add up to 27 minus 14, which is 13 as digits. No 4, 9, no 5, 8. It's 6, 7 as a pair, which eliminates 6, 7 in the rest of the column. So this can't be 6, this can't be 5, no 7 here, so this is a 5 here. That eliminates 5 there. 5 is value 4, which is in a 1 to 2 ratio with value 8. So this is 9. The 6, 7 pair eliminates 6, 7 in the rest of the box. So this is 1. There's no 6 here. We have 2, 4, 8 remaining in the rest of box 6. So 1 eliminates 1 here. That's 7. This is going to be 3 digits adding up to the hots, which is 18. We don't have 9 available because we can't have 2 reds here because then this 2x2 area would be all reds. So one of these is going to be red. One of them is blue. The reds have to be... we can't have... Okay. We don't have 3, 5, or 9 available. 8 cannot be here. Because if with that minimum, it would be 4, 6, and 7 for the hots, which would be 17 at most. So this cannot be 8 here. So we have to have 8 in the hots. That leaves 2 digits adding up to 10 for the remaining digits. No 1, 9, no 3, 7, no 2, 8, because we have a guaranteed 8 here, so it must be 4, 6, and 8 as the hots here, which means this can't be 4 or 6, it's 2. That eliminates 2 in the rest of the column and box. This can't be 4 anymore, it's 7, which makes that 4 there. That eliminates 4 in the rest of the box there. 7 eliminates 7 in the rest of this box here. This is 5 and 9. So 1 cannot be in the hot digits. It has to be 4, 6, 8. So this must be 4, which means this can't be 4, and the rest of the digits are 1, 6, or 8. 1 can't be here because of it has to be a hot digit. 4 eliminates 4 here. 6, 7 eliminates 6, 7 in the rest of the column, so that's 8, which makes this 2. That means this can't be 2 here. Remaining digit in column 8 then is a 1. So this is 1. That eliminates 1 here in the rest of this box. 8 eliminates 8 here. So this is a 1, 6 pair here. So these must add up to 18 for the hots. Can we have 3 hots here? I think the answer is no. If we have 3 hots here, that would be 4, 6, 7 plus 2, adding up to too much. So this cannot be hot. This is cold. Right, because it would be 4, 6, 7, 17 plus 2 is 19, when it can only add up to 18 at most. Can we have 2 here? Potentially. Okay, we have wall here. So this is value, it's 2 and 3, which is value 3 and 4. 3 could only be with value 6, and that would be a 5 as a digit. So this cannot be value 3 then. So this must be 3 there. That eliminates 3 from this column here and this column here. Remaining digits actually are 2, 4, and 8, right? In column 7. Yep. So this is 3. That's value 4, which is in a 1-2 ratio with 2 or 8. So no 2 or 3 here. It's 1 or 7. These are all odd digits. We have 3 odd digits here, a 4th odd digit here, and one of these is guaranteed to be an odd digit here for an even odd pair. So therefore, this cannot be odd. It's 6 or 8. which means this is a 1, 2, 7 triplet here. Interesting. That already adds up to 10. We know one of these has to be hot, because then that's too small of a sum. So this must be a red-blue pair. We don't know which. And the red has to be an 8 to add up to 18. So we're guaranteed this is an 8 here, which eliminates 8 in the rest of the row. So this can't be 8 here. Because 1, 2, 7, 8 adds up to 18 for the hots. 7 eliminates 7 in the rest of the row here. We have a 1, 5, 6 triplet, which eliminates 1, 5, 6 in the rest of the box. So this can't be 1, 5, or 6. It's 8. This can't be 1, 6, or 8. It's 7. 2 eliminates 2 here. We have a 4, 6, 8 triplet here. Actually, 8 eliminates 8 here, so that's 6. We have a 4, 8 pair in box 9, which eliminates 4 and 8 in the rest of the box, so this must be 2. The hot digits must add up to 18. We only have 16 right now, so therefore the 2 must be hot. And therefore that's a wall there. Remaining digits in row 9 are 5, 6, and 9. Remaining digits in row 7 are 3, 4, and 8. And 8 obviously has to be in the hot digit. This is an even odd pair here. 2 eliminates 2 here. Because of 2 in the row. 4 eliminates 4 here, so this is 3. That eliminates 3 in the rest of the box. It also eliminates 3 in the rest of the column here. Okay. So this is also a blue-red pair here, but we don't know which. Hmm. I'm guessing there's probably going to be red going this way. 4 eliminates 4 in the rest of the row. So 4 has to be one of these 2 digits here. Okay. Hmm. Obviously, this is a wall. Oh. We don't know. Okay. This could be three reds going that way. That is certainly possible. Hmm. Because it could be 189 going that way. Um. Hmm. What other restrictions do we have, really? I don't know. 8 is in the cold here. So the hot. Well, we don't know how many hots we have, though. That's the problem. If these are both cold, there's no way we can have 3 hots only here. So this would have to be hot here. Um. Hmm. Oh, that's interesting. We have to have at least 2 hots here, because otherwise there would be a 2x2 area here that would be all cold. So there's at least 2 hots here. So what happens? Okay, what happens if this is cold? If this is cold, that means hot has to go this way. You have to orthogonally connect the hots. This must be hot because of the 2x2 area. This can't be hot here, so this would have to be cold there, which would mean these would have to be hot to orthogonally connect because this is hot because of a 2x2 area. This would be diagonal of hot, so that would be hot. So we'd have 5 hots here. And we don't have 8 available. It could be 1, 2, 3, 5, 6, 7. That actually does, or 1, 2, 3, 5, 7, which adds up to 18. So that could work. Yeah, that would force this to be 6. This would be 8 and 9. That could work. Dang it. Okay, I was hoping that would lead to a contradiction. Oh. No, that does not work. Because these have to be. Yeah, that is leading to a contradiction. These have to be an odd even pair. If we have 6, 8, and 9, and we don't have 4 available, we don't have 8 available for the set of 5. So the only combination that works is to add up to 18 for 5 digits would be 1, 2, 3, 5, 7. But this has to be an odd even pair here. And the only even in that set is 2. But we already have a 2 in the row. So therefore, this cannot go hot here, because that forces this to be hot. We have to go hot this way. This must be cold. We must connect this way to hot. And this could go this way still, kind of. Maybe? I don't know. Can it? If we do that hot, then these both are hot, so this must be cold, which makes that hot. So we have the same problem. So this cannot be hot here. It has to be cold. So this is cold here. This is hot. We have a guaranteed, oh yeah, we have a guaranteed 4 here, a guaranteed 8 and 2. One of these is even, so therefore this can't be even anymore because we have all 4 evens accounted for in row 3. So this is guaranteed to be 1, that's guaranteed to be 6. Right. So this is 1 here, no 1 here, no 6 in the remaining digits here. These are all hot because, yeah, the hot cells must orthogonally connect. And this is too small now to just have these 3 digits. So we need another digit here to add up to 18. So then we have here, their boundary. This is a 2x2 area that's all blue, so we need a hot cell. That gives us boundary there. To add up to 18, you cannot have 2, 3, and 5 because that would require 8 here, and we can't have that. You could have 1, 3, and 5, and 9, and you can't have 1, 2, and 3 here because that would be too small. That would require a digit of 12. So this has to be 1, 3, and 5 here, which eliminates 1, 3, 5 in the rest of the row and box. So this can't be 1 or 5, it's 2. That means there's no 2 here. It's 1, 6, 9 as a pair, as a triplet, which eliminates 1, 6, 9 in the rest of the row. So this is 2, 8 as a pair. That leaves this as a 9. We have to have 6 and 7 here then. 9 eliminates 9 in the rest of the row. 6 eliminates 6 in the rest of the row. These have to be odd and even. 2 is a odd value, so we must have an even value here, which is a 5, which makes that 4 there. That means this can't be 4. It's 9 and 4 there. No more 4 in the column here. We don't know. Okay, so this is boundary here. P must go this route. We don't know which route, though. This way or that way. This is value 4 minus 1, which is 3, so that must be in a 1 to 2 ratio with 6, so that's a 7 there. No more 7 in the column. For the colds here, we have guaranteed 3, 4, and 7. That doesn't tell us too much. 9 here eliminates 9 in the rest of the column. This is hot, this is hot. This is a diagonal of red, so one of these is red, the other is blue. Don't know anything about this. Remaining digits of, let's do column 1. We have 169 with 3 or 4. No 1 here because of 1 in the box. 3 is eliminated from this cell here because of 3 in the row. Okay. We are guaranteed 8 has to be one of those 2 digits. Row 4, we are left with 3, 4, 5, 6, 8, 9. No 9 here because of 9 in the column. No 3 here because of 3 in the column. No 4 here because of 4 in the column. Okay. So we could have 3 reds here and the rest are blues. That is possible. Can we have red go here? If this is red, that forces this to be blue, which would force that to be red to orthogonally connect. That would leave the rest of these as blue. So that would force this to be red because this would be 3 blues there. That's possible. Yeah, that seems possible there. No, that doesn't work. So if we have a red here, that forces this to be blue. Therefore, that's red. We'd have 5 reds in this box without a 1 in those hot boxes. And the minimum then would be 2, 3, 4, 5, 6, which adds up to 20 for the digits, which is too large. So this cannot be red here. It must be blue. So this is a diagonal. Anyways, if this were red, this would also have to be blue, no matter what. But we now know this is blue. So this is blue, that's blue there. We have wall there, wall here. The red must orthogonally connect, so it has to go that way. We have wall there. The red, I guess it could orthogonally connect this way, so that's fine. We have a diagonal here, though, that's all red, which means it must orthogonally connect this way. So that's red, or it can't have a diagonal of blue across the red. This is 3 reds, so that's blue here. That's also blue here because that's too many reds if we have reds there. So these are walls. This is a diagonal of blue, so this cannot be red here. So this must be blue, which means this can't be blue. That's red. This is 3 red, so this can't be red here. It's blue, which means this can't be blue. That's red there. Diagonal of blue, so we have to have blue there. We don't know if it connects this way or if it connects this way. It could connect to either way. I think, right? We have wall this way. So... Oh. No, we can't go this way. Because this is a wall, right? So then if this is the red, that forces this to be blue to orthogonally connect, but then P doesn't have access to the cupcake. So therefore, this can't be red. Therefore, that's blue, which means red does have to go that way. And we are done with the cold and hot regions. This then must be 1, 8, 9 to add up to 18. That eliminates 1, 8, 9 in the rest of the box and column. So this can't be 9. This is 6. This can't be 6. It's 1. This can't be 1 or 6. It's 9. This is 3, 4, 6. As 6 eliminates 6 here, so it's 5. This can't be 5. But this 3, 4, 6 triplet eliminates 3, 4, 6 in the rest of the column and box. So no 6 here. 3, 4, 6 eliminates 6 here, so that's 1, which makes that 6. This must be 8 to add up to 18, so that's 4. These 5 digits add up to 18, and therefore we need a 1 there. And it cannot have a 9. And we can't have a 6, because it has to be either 1, 2, 3, 4, 8, or 1, 2, 3, 5, 7. So we're guaranteed a 2 here and a 3 here, with 4 or 7 being the rest of the digits with the 5 or 8 there. No 3 here. This is guaranteed to be 2, so this can't be 2. That's 5, which eliminates 5 here, so it's 2. 3 also eliminates 3 in the rest of the row, so this can't be 3, which means this is 3 there. There's no 3 there. 4 eliminates 4 here, and eliminates 4 there. 5 eliminates 5 here, so this is 9 and 5. 5 eliminates 5 here, so that's 8. So this must be 1, 2, 3, 4, and 8, adding up to 18 here. So this is 2, this is 3, that's 4, which eliminates 4 here, so it's 6 and 4. 9 eliminates 9 here, so it's 8 and 9. 8 eliminates 8 here, so it's 2 and 8. 1 eliminates 1 here, so it's 5, and 1 here, so it's 7. 7 eliminates 7 here, so it's 6 and 7. There's no 4 or 8 here. This 5 eliminates 5 in the rest of the row, so this is 5. No 5 or 6, it's 9. 8 eliminates 8 here, so that's 4, which makes this 8. 4 eliminates 4 here, so it's 8 and 4. 5 and 6 here, eliminate 5 and 6 in the rest of the column, so that's 9. This can't be 7 or 2, so that's 1, which makes that a 2 there. 6 eliminates 6 here, so it's 5, which makes that a 6. 1 and 5 eliminate 1 and 5 here, so that's 3, which makes this a 1. 6 eliminates 6 here, so it's 7 and 6. That leaves these as a 5 and a 7. Experiment completed successfully. Test date, April 8th, 1975. Cells visited 75, black currants eaten 12, red currants eaten 4. Experiment 33 had only just concluded when the lights above me began to flicker. As I looked up, a sudden loud electrical hum echoed from somewhere down the corridor, followed by a yell that could only have come from one person. Before I had time to react, he stumbled into the lab, clutching his chest. Unsteady on his feet, he staggered towards me and placed his uninjured hand on my shoulder. For a few moments, he held my gaze, his expression pained and urgent, trying to form words, but none would come. His remaining strength gave way, and he buckled to his knees before collapsing sideways onto the floor. The humming noise faded, and everything was suddenly still. And so the paths here are obviously this way. And then, oops, what just happened? Did I delete path? I guess I did. And then the other path is just going all the way around. Oops. This way, here, to here, to here, to here, to here, to here, to here. And those are the paths. Interesting. Was making a use. Yeah, I didn't realize that the hot and cold regions had to be the hot. Yeah, they were summing up to the same sum no matter what, no matter how many digits they had, which was interesting. I didn't expect that actually at all, so that was interesting. And that was definitely necessary to solve this puzzle, because otherwise you weren't going to be able to solve it without that. So, very interesting puzzle. Anyways, I hope you enjoyed this solve, and I'll see you next time on Frank Puzzles. Take care.